Hello, everyone. Welcome to the CPCI Fifth Edition Design Manual Chapter 2 webinar presentation. My name is Ariane Sabourin, and I am the Marketing Manager for CPCI. Today's presenter is Wayne Kassian, Principal at Kassian Dyck Associates, and Editor for Chapter 2 of the CPCI Fifth Edition Design Manual. Wayne Kassian will present the significant changes to Chapter 2 and will highlight the seismic design examples in the earthquake design and analysis section of this chapter, which has been modified to reflect the changes in the 2015 National Building Code of Canada. Before we get started, we would like to acknowledge the gracious support of our CPCI member sponsors of the Design Manual webinar series. Thank you to BASF, JVI Inc., MCM Industrial Consultants, and Ultraspan. It is this type of support from our members that assures CPCI can continue to develop and deliver high-quality programs and services such as this, and to build on our body of knowledge for the architecture, engineering, and construction industry. So without further ado, I will now turn it over to Wayne Kassian for the presentation. Thank you.
So I'll be reviewing Chapter 2 of the CPCI Design Manual, 5th edition. Our agenda really is to discuss the significant changes from the 2015 National Building Code with relation to seismic, but I'm also going to give a summary of just Chapter 2 itself, just to go through some of the important aspects of this particular chapter. So with respect to the seismic changes in the new design manual, it's based on NBC 2015, and significant changes have taken place due to the improved understanding of the seismic hazard across Canada. So basically, there's been a lot of data and research done in recent years, and the seismic provisions have now changed considerably. There's new provisions for low hazard seismic design, buildings with flexible diaphragms, buildings with inclined columns, and they've also added base isolation and energy dissipation systems and rock foundations. So we'll be talking about all these seismic changes, but before we do, we'll kind of go through from the start of Chapter 2, just highlighting what's in this portion of the manual. So with respect to precast concrete, obviously several advantages of using precast concrete construction, one being construction speed. Products are built and prefabricated off-site and then brought to site and erected in an efficient and quick manner. Also, good quality control with workers working in a plant environment, and in fact, that's recognized in the Canadian Concrete Design Code, CSA A23.3, where precast that's produced in a certified facility is given a Phi-C factor of 0.7 compared to cast in place. So it is recognized in the design code that precast concrete coming from a certified plant does have enhanced quality control. Obviously, concrete is fire resistant and durable, and by pre-stressing our structures and our members, we're allowable, we are permitted to get allowable spans much longer than you can with cast in place construction. Architectural precast concrete, very attractive in a wide variety of finishes, so we can provide different shapes and different colors, different types of finishes in precast, and also good thermal and acoustical control, and obviously all-weather construction. We don't have to be shut down when we're a precast plant due to poor weather, and projects can be built on site by trucking and craning pieces and continuing through winter construction without worrying about heating and hoarding on site. So in Chapter 2, there's a section on preliminary analysis. Now, Chapter 7 has some design tables to help people sort of look at different member sizes and different spans and types of members to be used in structures, but there's some general guidelines given in Chapter 2. Obviously, when we're dealing with precast structures, we try to optimize the framing dimensions to have as few pieces and as large pieces as possible, respecting site crane limits and trucking and shipping restrictions, but you get your best economy with any precast structure by reducing the amount of pieces that you have to transport and erect. There's some just general tables in Chapter 2 giving some span to depth ratios for hollow core and double T's and beams. And if you look at this slide, you really get a feel for, based on the member or element thickness, how far it can span if it's pre-stressed. So, hollow core floor slabs, 30 to 50, double T's 25 to 40, and depending on actual loading conditions and specific design criteria, you can push these limits a little bit, or you might have to be under these a little bit. It really depends on the detailed design, but these are good numbers to keep in the back of your head for proportioning pre-stressed elements in a building. As compared to cast in place, if we look at CSAA 23.3 table 9.2 for the thickness, like the height of structural cast in place, one-way slabs or beams have a ratio to the clear span of only 16 to 20 based on the criteria of having elements that are not subject to causing cracking with the interior finishes and that type of thing. So when you compare these ratios of 16 to 20 to the, sort of 40 to 50 that we can get out of pre-stressed, you can really see the advantage of being able to do long spans with precast pre-stressed structures. There's a section in the manual on expansion joints, and although everyone refers to them as expansion joints, it's really common that they experience contraction and shrink more than expand. You obviously need in a building, as the length gets too large, to be able to relieve and ensure that the stresses and strains caused by temperature changes and creep and shrinkage are not causing distress and cracking to the structure. So expansion joints are put in to relieve that and divide the building up into smaller sized portions. And although we do call them expansion joints, depending again on the temperature change and the effects of the building, but more often than not, these joints are actually undergoing opening rather than closing. So they really do become joints that are pulling due to temperature change, but restrained creep and shrinkage is a major effect. And obviously, when you have separated your structure into two different portions with an expansion joint, you obviously have to satisfy the code requirements for the separation between them to account for wind and seismic building deflections as well. In Chapter 2, there's this traditional historic table to help designers choose how long you can go in your particular temperature area of the country with respect to looking at the spacing of expansion joints. And I put a red arrow on the modification factor note on the left of this table that's in the manual because it provides some additional criteria. You can't just look at this chart yourself to sort of get a feel for what would be a reasonable length to go without an expansion joint in a building. You have to apply the applicable modification factors to this table because that table is based on, beam column construction, thinking the structure is hinged at the base with a heated interior. So there's different factors. You have to apply coefficients or modifications to the values that come out of that table to account for if it's a continuously air-conditioned enclosed building, they say that you're allowed to increase those lengths by 15%. However, if you're a parking garage, such as an outdoor unheated parking garage, they would recommend in that table decreasing the allowable length by 33%. And again, if you have fixity at the column bases, applying another reduction in the length. So when you're looking at expansion joints and dividing a structure up to limit the effects of temperature change and creep and shrinkage, you really do need to analyze the type of connections, how stiff the columns are. You need to look at the relative stiffness between beams and columns, and obviously weather exposure conditions as well. So a detailed volume change frame analysis will provide the best and most accurate expansion joint requirements. So you can analyze your structures and look at what's happening and see if the stresses and the moments and shears that are being developed due to these effects are acceptable with respect to your design or not. And obviously the last bullet point, spacing here. Joint spacing is sometimes determined based on experience with a particular type of structure. I know PCI in the United States, and although they would potentially have different climatic conditions than in Canada, has some documents permitting expansion joints in parking garages that would probably exceed the value coming out of our CPCI design manual table. So it's all needs to be looked at and engineered, and definitely Chapter 2 can provide some very good guidelines as a start of looking at your recommended spacing of expansion joints in a structure. A large part of Chapter 2, which as precast and pre-stressed engineering goes, that the cast-in-place concrete designers generally don't have to look at in too much detail, but it's a large part of designing precast buildings and other types of structures like parking garages, is really looking at the strains resulting from creep, where, concrete under sustained load, whether it be the pre-stressing force that's sustained or the deflection, it will soften and continue to either shorten or deflect due to creep until it becomes stable. Obviously, concrete is shrinking as it loses moisture and over time, and those strains need to be taken into account, and either increases or decrease in temperature change will make precast concrete elements expand and contract, and all of those features need to be considered in a design of a total precast structure. And there's several examples in the CPCI design manual covering how to look at all those strains and the resulting effects. What can happen is you can generate very large connection forces, you can affect the service load behavior, and ultimately the capacity of the elements in the precast structure due to restraint forces. So you really need to be careful looking at the effects of creep, shrinkage, and temperature change in precast, total precast buildings. So there's a small section on diaphragm design in Chapter 2 where you have to look at the horizontal loads coming from either wind or earthquake and how those are getting transmitted to your lateral load resisting system through the roofs and floors, and those roofs and floors act as horizontal diaphragms or horizontal kind of plate beams, in essence, transferring either your seismic loads or the wind loads that are acting on your structure to the lateral load resisting system, whether that be shear walls or moment frames. And, hollow core can be designed as a diaphragm, in this case, transmitting the loads to the interior shear walls or exterior shear walls or elevator and stair shafts, depending on the design of the structure. So we want to use these diaphragms to get the load from where it's applied to the lateral load resisting system. So this diagram's been in the CPCI design manual for years. It's a very simplistic analysis of a diaphragm, looking at it as a horizontal beam spanning between the two red arrowed walled supports there, saying, well, if you've got a lateral load, whether it be from earthquake weight of the floor and the wall structure, or wind blowing on the outside wall, acting as a simply supported beam, in this case spanning between the shear walls or the supporting walls, and essentially you have your shear and moment diagram just coming from structural analysis, and you have to look at designing that system because it's not a monolithic concrete diaphragm. It's made up of double T's or hollow cores or slabs or other elements that we need to join together to act as a big beam spanning between those supports. So traditionally, precast structures have been designed assuming that that floor system acts as a rigid diaphragm, but really recent and ongoing research into diaphragm behavior, particularly with longer spans, suggests that a more refined method may be appropriate for looking at your diaphragm design and the distribution of load to the lateral load resisting system elements. So with the traditional horizontal beam analogy, you basically consider your roof and your floor system that's made up of individual precast members as a deep horizontal beam analogous to a large plate. The shear walls or the moment resisting frames can be the supports for that beam, and lateral loads are transmitted to these supports as structural reactions. And then obviously if you have a beam, you have top and bottom chords that are subject to either compression or tension, and you can have load reversal with lateral loads. So you have to look at designing the diaphragm basically for the shear and the moment that are coming from the structural analysis, and you will end up having tension and compression chords on the outside faces that are resisting the required loads from the analysis. So shear in that beam analogy must be transferred between adjacent elements to the supporting elements. Web shear, your shear flow must be transferred to the chord elements. And because we're dealing with all these individual pieces and we're trying to tie them together to act as one big beam spanning from support to support, diaphragm design is essentially a connection design solution. So really the difficulty with designing diaphragms for precast engineers is, compared to cast and place floor slabs where it's monolithic concrete and you can design the overall behavior and reinforcement of that type of diaphragm. With precast, it's made up of individual elements, so we need to make sure we've looked at all the proper force transfer to connect all the elements together and provide the required moment and shear capacity throughout the whole diaphragm. So some structures may require more detailed and complex diaphragm analysis than others. You should consider openings, discontinuities, and geometry changes. So really the simple beam analogy may not always apply. In some situations, strut and tie modeling may be more appropriate. And, PCI has been publishing different papers and there's been different research papers presented on how you can analyze diaphragms using finite element analysis, where you look at the stiffness even of the connections between the precast pieces and the overall diaphragm, and really need a proper structural engineering analysis of the diaphragm to get the load transfer. Basically, you're trying to take the loads from where they're applied and get them to the supports so they can get down into the foundation, and just following those loads properly through. So yeah, you need to do an appropriate analysis for your type of structure and conditions with respect to diaphragm design. I put this slide in. This is not in the manual, but I've had several questions coming to me lately about the design of diaphragms. Why in CSA A23.3 there's the diaphragm section in the seismic portion of clause 21, and there's two different limits, one for cast and place construction, which is this equation 2119, which is related to monolithic cast and place diaphragms, and then you go down the page in A23.3 and you get to another equation which applies to precast systems. And really what's happening here, people are wondering why there's different limits under the clause 21 seismic diaphragm system categories between cast and place and precast. So I put this slide in for the participants watching just to have a look at equation 2120. If you actually look at the shear capacity for the diaphragm in that equation, you'll see that there is no concrete contribution, whereas for the cast and place equation 2119 above, you see there's a concrete contribution and a steel contribution. And the reason is A23.3 14 adopted this from ACI 31802 provisions. The precast system limit of 0.6 and having no concrete contribution for this particular diaphragm. This equation 2120 was really intended for what I'll call a thin topping, 50 millimeter, 75 millimeter, maybe topping on top of precast elements. If you were going to use the topping as a diaphragm, basically the feeling is crack control joints would be put in over top of the precast element joints. So the topping really has saw cuts or control joints mimicking the joints in the precast. So it was felt coming from the commentary in ACI 318 2002, the provision was put in to basically neglect the shear capacity of the topping diaphragm over precast members when it's thin, and only have essentially the reinforcing shear friction type contribution to that equation. So that's the big difference. Obviously, if you're putting in a very thick concrete topping on top of your precast elements, and you as the engineer can justify a concrete contribution, and it's not a cracked thin topping with joints that would maybe open up and not be able to resist load in a seismic situation, you would use your own engineering judgment and perhaps not apply equation 2120, look at 2119 again, depending on the thickness of that concrete on top of the precast system. So there's a section in the manual on moment resisting frames, and it's simpler to have connections that allow movement and rotation, but if you need a moment resisting frame, there's some examples there of how to handle that. And I guess the big picture coming out of that is you really want to limit the amount of moment resisting frames if you can. I mean, we prefer to use shear walls, but sometimes due to architectural requirements or openness requirements, you can't use shear walls in your building, so you still have to provide lateral stability. So you could use moment resisting frames or fixity at column bases, or a combination of both to resist your lateral loads. But general rule of thumb, you want to keep the amount of moment frames to a minimum and locate them near the center of your structure to reduce those volume change effects. So there's a really good resource and example and graph in the CPCI design manual showing how to deal with flexibility of footings and fixity at the base of columns and cantilevered columns. That's a very good engineering resource. And then also some examples showing, if you have a moment frame, just how large the moments and shears are that can be developed as your frame gets larger. So if you look through the examples in the manual, you'll see that due to volume change effects and having restraint due to fixity, either from column bases or from moment frame action, you actually generate very large moments and shears as a result of volume change, not from your structural loads. So in general, you have to be very careful when you're looking at designing moment frames and taking into account the effects of temperature changes and volume changes and creep and shrinkage as well. In precast, it's most common to use shear walls, and they're sometimes just solid walls, sometimes they're parts of shafts or cores or elevator stairwells, and again, the design engineer decides whether he's using the entire stiffness of those cores and properly connecting all the individual walls together to act as that composite stiffer box type unit, or if they're individual walls not connected together. And again, it really is a function of the design. Shear walls act as vertical cantilever beams, transferring the force, and there's several examples in the manual looking at the lateral load design for shear walls and whether they're tied together, acting as coupled walls or not. And then a portion proportioning the lateral load to the shear walls. You have to really look at your structural system and do an analysis to determine how much load is going to each shear wall. The example in the manual is really showing the traditional sort of rigid body effect of if you had a very rigid diaphragm, in this case with 4 walls, and you were pushing it and all of those walls move the same amount. It's all of your shear walls are the same height, same stiffness, and they all deflect the same amount. As shown on the left, you would have equal reactions in each shear wall. As soon as your seismic loads, such as your applied load at the center of mass, doesn't equal the center of rigidity, you get rotation with this rigid diaphragm type analysis, and then your reactions, as shown on the left, are not symmetrical anymore due to that rotation of having your seismic load offset from the center of rigidity. So that type of analysis is shown in the manual, but some structures definitely require a more detailed and complex analysis to consider openings and discontinuities and geometry changes. So that simplified approach might work for some structures and would not for others. And again, just a quick tip when you're designing shear walls, again, we're creating them not as a monolithic cast-in-place walls, but as wall segments tied together, either vertically or both vertically and horizontally. And you have to design the connections between all of your different shear wall elements. If you're transferring load around corners or vertically from panel to panel, you need to properly account for all the shear and moment transfer between all the individual panels to get the structural behavior that your analysis is based on. There's one section at the end of Chapter 2 on segmental construction that could apply to post-tension tanks or post-tension trapezoidal box girders, has some good information about joints. Post-tensioned segmental construction is when you're tying the individual segments together on site. With post-tensioning, there's some simple design procedures. It's basically the same as precast, except you have additional items to consider, such as settlement and shortening of scaffolding due to dead load. Segments need to be carefully aligned and leveled before you do the post-tensioning, and you really need to look at additional items such as the tension between segments, the joint shear, relative displacement at joints. Very important to look at post-tension bearing and anchorage to make sure you're not getting cracking or high tension stresses, and that you're following proper reinforcement details in the anchorage zones, and really need to be careful looking at deflections. So again, Chapter 2, Section 9 has some information about segmental construction. Now I'll get into kind of the main rest of the presentation is really talking about Section 2.8 on earthquake design and analysis. Len Dutrisac from the Cement Association of Canada really was the seismic editor for this portion of the manual, and the previous manual was based on the 2005 NBC, and now we're up to the 2015 NBC. Dennis Mitchell, along with Patrick Poultry, both professors, did a paper back in 2010 with the Canadian Society for Civil Engineering, a paper that explains the evolution of the seismic design provisions in the National Building Code of Canada. So if you're interested in looking through how earthquake design has progressed in the last 60 or 70 years, Dr. Mitchell and Dr. Poultry, and along with other authors, have a paper available through the CSCE that shows the history. But really, the 2015 NBC has had considerable changes in the seismic portion, mainly due to a better understanding of the contributors to the seismic hazard, and looking at more data that became available on ground motions. So really the whole seismic section in NBC 2015 has had quite a few changes. So things that are new, there's new design requirements in low hazard zone. So for low seismicity, there's new requirements, updated seismic data, whole bunch of new structure period dependent site coefficients. So I'll explain that. Revised formulas for calculating the spectral acceleration values. Added another type of structure irregularity. They've revised the higher mode and base overturning reduction factors, so I'll explain that, and also have changed the cutoff formulas for calculating maximum static base shear. So if you have any internal office spreadsheets and design tools that are currently designing to the seismic loads, that'll be undergoing significant changes to incorporate the new seismic provisions and equations. So there's also revised minimum base shear for walls, coupled walls, and wall frame systems, new foundation design provisions, new provisions for seismic isolation and energy dissipation provisions. I haven't been involved myself with a project in Canada that's used seismic isolation with a total precast structure, but have in a California project. And again, buildings with flexible diaphragms is also included in the new NBC. Obviously, structures still have to be designed with a clearly defined load path, and you design for 100% of the earthquake load and carry that through from its point of application down into the ground. So that obviously hasn't changed, but there's a new simplified approach. Some new equation that's come in. Basically, if you are designing in an area of low seismicity, you now have a simple approach that you can follow through. And I guess one difference is the NBC now has seismic design throughout all of Canada. And basically, I think experience has shown that, even in the prairies and middle area of Canada where it's been considered to have low seismic activity, you can still get large earthquakes. It's just they don't occur very often. And I guess looking at the seismic hazards and that type of thing, basically, I know from even the Christchurch earthquake in 2012 and going back to the Kobe, Japan earthquake and others that were in areas of just moderate to low seismic activity, it's really shown that you can get earthquakes, and if they're close to an urban center, it can cause considerable damage. So I think the 2015 NBC has really looked at other at things that are happening in the world as far as earthquake and seismic activity, and it has really made a lot of changes. But the one is these triggers for the simplified approach. If you satisfy these equations, then you can go through and follow some new procedures where you have a new equation to use, where you don't get as complicated as far as figuring out your FS and SA values. Don't have an RD R naught to look at. There's an RS value that you can look at using, which is 1.5 or 1, and it's just a more simple to use equation for these areas of low seismicity, as long as you fall within the requirements of those two triggers, the 0.16 and the 0.03 value. And I guess really the 0.2 trigger implies that a building in a low hazard zone such as Winnipeg, could be designed using the simplified procedure basically. And, I had looked at these values for Calgary with the 0.16 and the 0.03, and I think we would exceed these values, so we would have to use the full design approach, not the simplified approach locally here. And then looking at the equivalent static force procedure, you can obviously always use dynamic analysis, but Chapter 2 goes through and shows the equivalent static force procedure. Regular structures less than 60 meters in height, and following through, as long as you satisfy any of those criteria, you're allowed to use the equivalent static force procedure. And then this is similar to the previous National Building Code, the types of irregularity that are permitted, although the new NBC has added type 9 that's not shown because it got cut off on this table, and I didn't want to make the text too small to read, but just for gravity-induced lateral demand irregularity, so that'll be familiar to the engineers that have done that design before, but some new stuff has cropped in. So the equivalent static force procedure, similar equation for the lateral earthquake force V, new requirement for walls, coupled walls, and wall frame systems. A new limit is put in, the S4.0, and again for moment resisting frames, the S2.0. And again, we'll talk about it later, but notice in this shear equation, there's this MV to account for higher mode effects, which is similar to the previous NBC, but I'll mention that a bit later, that we do still have the MV in the base shear, but there's new tables for it as well. And then this is a little bit new, these maximum cutoffs for your shear. They were basically put in, I guess, recognizing that short period structures usually have like more reserve strength, and I guess the NBC 2015 allows such structures with short periods to have the 2/3 base shear cutoff, and as long as you have, it being detailed with a bit of ductility, and so that's where the 2/3 is coming from. And then I guess they realized that cutoff could cause some complexities for longer periods, so they also have the 0.5 equation in there as well. This is basically the same as before for the site class, and again looking at the properties in the top 30 meters of soil, although now they're adding the 30 to clarify that in the subscript of the S bar here. And then this is all new, which looks scary to those who are looking at it. And basically now this FT site coefficient is new. They got rid of the FA, FV. The FA in the past for short period and FV for long period have disappeared. And now we have all these different values that are coming from up to a 10-second period, basically. And I'll explain that as we look through, but it's new spectral response accelerations. So there's several tables in the CPCI manual now for both F.5, 1, 2, 5, and 10 that look like this, and they are all now a function of site class. Site class C is always the reference, so you'll see it has 1s. That's the sort of the reference soil used by the NBC, and then the factors either go up or down from there. So that's a new F value that needs to be used in conjunction with the peak ground acceleration reference and the peak ground velocity, and basically the probability, the 2% probability of exceedance in 50 years is still the same, which I think was a period of 1 in 2,400 years or something like that. But basically just the approach has changed due to the additional understanding of the earthquake effects in soil. So now really have to look through all these equations for the type of soil, and those are all provided in your manual from the NBC with permission from National Research Council to be reprinted, and obviously still use linear interpolation between those values. And then new tables for F peak ground acceleration varying with the soil. Same with PGV, peak ground velocity varying with the soil. So these are all new, and importance factors have not changed. Still have the RD, R naught factors allowing for ductility and overstrength basically, and I think that's still the same, although a few values and some limitations have changed in the NBC table. And I guess basically the RD is the capability of the structure to, dissipate energy through plastic inelastic behavior. So it's really a measure of its ductility, whereas RO, the overstrength, is really accounting for the reserve strength. So that needs to be taken into account. This table, similar to before, just with a few revisions. So you still use the RD and R naught based on your type of lateral load resisting system. Distribute FT at the top for higher modal effects. That's still in the NBC, so that hasn't changed. So you basically calculate your seismic loads, and you have to apply your FT value at the top of the structure. So that's similar to previous. Distributing the load between the floors, so you take your total shear minus the FT that you put at the top, and you're distributing that as before. But that equation obviously is just based on first mode behavior, and we know other modes can have some effects. So we're distributing the lateral earthquake loads on the different floor and roof levels as per this equation, but we need to make some adjustments to that. As I mentioned, our base shear had included that MV value, and now we have to say that we also have to look at a J value because the moments that are created due to the shear, it's been found that because we bumped up our design shear, our FX forces at every level, to account for higher mode effects, those really don't affect the overturning moment on the structure. So we also need to take into account this J to get a bit of beneficial reduction on our overturning moments that were maybe overestimated by including higher mode effects. So again, new table for MV and J. Basically, MV is bumping up the horizontal loads that you're designing for shear, for your diaphragms, and the loads at each level, and J is a reduction in your moment due to the fact that they believe that the higher shears that you need to design for due to higher mode effects, that overturning moment really shouldn't be affected due to higher mode effects, so then they give a reduction. So again, that all needs to be worked through. Similar to previous, obviously, if you have torsion in your structure, you need to consider that. With respect to where the applied seismic load at the center of mass is occurring and where your lateral load resisting elements are, and still look at accidental eccentricities, so that really hasn't changed. And again, just looking at the simplified diagram from before, when your earthquake load, if it's applied at the center of mass, it doesn't coincide with your center of resistance or your center of rigidity, then you get a torsion, but you're also forced to look at minimum eccentricities and ensure you're designing your structure for unanticipated torsion as well. And then just a reminder to everyone, even though you've done a lateral load analysis on your computers or however you're doing it, the deflections that you get out of your analysis, you still have to multiply by RD/R naught over IE. So just a reminder that you need to magnify your deflections from your analysis to get realistic values of the deflections in the earthquake. And still the same drift limits as before, 0.025 times the height of your structure or floor-to-floor height, again for typical buildings. And again, same structural separation where you have two structures, could be at an expansion joint or adjacent structures, allowing them to sway in the earthquake. And you can use the square root of the sum of their individual deflections. Remember to magnify the deflections as we just mentioned. And then some additional design provisions for diaphragms. Need to make sure that the connections don't yield, and the design obviously needs to account for the shape of the diaphragm, including openings. Just some additional reminders, not new, but just reminding everyone, you need to increase your forces to reflect the lateral load capacity of the seismic force resisting system. So you determine your loads, but you also need to look at your capacity as required by the different provisions in your concrete standards and the NBC. And, as far as the load going to the floors, your minimum is your shear divided by N, the number of floors at each level. So I guess it's basically looking at the forces in your diaphragm and either magnifying them based on the capacity of your lateral load resisting system up to the limit of your shear divided by the number of stories. And then what hasn't changed really is still for architectural cladding or elements attached to the outside of the building. This equation will look familiar for determining your seismic loads on cladding. So that's the one section that really hasn't undergone changes per se, still has sort of the same table, although they've added some more categories to it. But in general, I feel precast would fall under the exterior walls, or if you had something near the top where it might be a cantilevered parapet, you can use your engineering judgment for the type of elements that you're looking at as far as which category goes to determine your coefficients and factors to be used in your equations, so that really hasn't changed. And then basically, the seismic provisions in 2015 MBC have been totally changed. Still, the manual provides the basic guidelines for you to look at how to apply those provisions to precast structures, whether it's a hollow core or double T parking garage or hollow core building or architectural cladding. So it's a very good reference to assist engineers with looking at how to design precast concrete structures. So with that being said, I will turn it back to CPCI.
Great. Thank you for this very informative presentation, Wayne. So please mark your calendars for the upcoming webinar presentations. The next one for Chapter 3, Design of Elements, will be held on Wednesday, June 20th. I would also like to thank our Design Manual webinar series sponsors once again for their support. BASF, JVI Inc., MCM Industrial Consultants, and Ultraspan. And at this time, I'd like to open it up for questions. If you have any questions about today's presentation, please type them in the Q&A box that appears on your screen, and I will turn it over to Wayne again.
Okay, I see we have a few questions here, and I think we have time to go through them. One was asking if the NBCC 2015 is fully in effect now, and I guess not across Canada. So what happens with the National Building Code is it's really a model code like the fire code and energy code, and it's basically adopted by provinces or territories. And just due to the timing of the provincial codes, I guess I understand even in Ontario, the next Ontario Building Code won't even come out till 2019. So although the CSAA 23.314 and the NBC 2015 have been out a long time, these codes won't even probably be used in Ontario until 2019, whereas other provinces, like if the Atlantic provinces or other provinces that don't have their own provincial code, like Alberta, BC, Ontario, and Quebec, then when they adopt the NBC, it would come into effect. So really, the timing of when these provisions are to be used is really a function of your province that your project is working under. Another question, just have earthquake loads using NBC increased or decreased? I guess I've read a few things that have said, from insurance companies saying that Vancouver Island was very high seismic before and now it's got even higher. I think the Yukon and Northwest Territories have had an increase in seismic hazard. I think Ottawa maybe had some reductions down. So I guess really depending on what the soil you're on and looking at what's happened across the country, I wouldn't think of it as well as earthquake going up or down. I would think it's more of based on getting more seismic data, they're determining more appropriate design for different areas of the country. And another question, can hollow core be used as a diaphragm? Again, depending on the seismic zone you're in and the requirements in A23.3 and the building code, you can certainly use a hollow core as a diaphragm. You just need to obviously design it appropriately, but it can be used as a system to provide a diaphragm. Just needs to follow the applicable provisions of the codes and standards. Ductile shear walls with precast concrete wall panels, practical to construct and design in high seismic regions. So basically with ductility, you design for lower forces. So the higher your sort of RD, R0 factors, you're designing your concrete elements with more and more rebar detailing to allow, that energy to be dissipated and to be able to undergo the deformations without breaking and just be very ductile as far as how it operates in an earthquake. And I think certainly, compared to cast in place construction, you could certainly detail the reinforcing and follow the applicable requirements in the concrete standard with precast just as good as cast in place. I guess I had another question where I was talking about the concrete diaphragm topping over top of the hollow core being a different shear limit compared to cast in place, and just saying, well, if you make the decision to use the cast in place equation rather than the precast one, is that not against the code? And my answer would be you need to be comfortable with what you're doing as a design engineer, understanding what the intent of the code clauses are, and following the codes as applicable to your particular project. So I guess that's just a generic question. So I guess that's all of the questions that I see that we have, and that would be it. I'll put it back to CPCI.
So that concludes the Q&A session and the presentation for today. Thank you again, everyone, for taking the time to join us, and we hope that you enjoyed the webinar. If you have any additional questions for CPCI, you can contact us at info@cpci.ca. Thank you again, and have a great afternoon, everyone.